Welcome to today's iCANX lectures. I'm Paul Weiss from UCLA, representing our organizers Alice Zhang from VEDA and Jagadish from ANU. And it's my very great pleasure to host today's iCANX talk, our final talk of March. We have Professor Naomi Halas from Rice University today. As you've seen over the last month, we've added panelists and young scientists to have a conversation with our speakers, and we're delighted today to continue that tradition. So our lecturer today, Professor Naomi Halas, is the Stanley Seymour Professor of Electrical and Computer Engineering at Rice University, where she's also on the faculty of the departments of physics and astronomy, chemistry, materials science, and nanoengineering and bioengineering. She's a pioneer in nanoscience and nanotechnology, particularly in nanophotonics, addressing fundamental issues and applications from biomedicine to water treatment to plasmonic photocatalysis. She's been elected to the National Academy of Science, the National Academy of Engineering, and the National Academy of Inventors, and is a fellow of the APS, OSA, SPIE, IEEE, MRS, and the American Association for the Advancement of Science. She's received a great number of awards, including the Frank Isaacson Prize and Julius Lilienfeld Prize of the APS, the R.W. Wood Prize of the OSA, and the ACS Award in colloid chemistry. Professor Halas and I ran parallel tracks, and I knew of her long before we had a chance to meet when we were both postdocs back at Bell Laboratories. And it's been a great pleasure over the many years since to have time together with her and to talk about science and where she sees her work and our field going. And so it's a particular pleasure to introduce Professor Naomi Halas for today's iCANX lecture. And I will turn the floor over to you.
Okay. Do people see my screen?
I don't see it coming yet, but sometimes there's a little bit of a delay.
Their screen.
Here it comes.
Okay, and we get into presentation.
Mm-hmm.
Okay.
Perfect.
Great, thank you very much, Paul. It's great to join everyone today. I'm going to talk to you a little. So what you're seeing here actually is one of the buildings at Rice University where we spend most of our time and where my students spend most of their time. I'm going to talk to you today about nanoparticles and light in the context of several applications that we have been pursuing really for the past 20 years. But they have impact on society. Some of them also address some really critical issues in sustainability as well as in human health. So I have plenty of stories to tell, so I'll get started. So metal nanoparticles and light have a very interesting interaction. The conduction electrons in metal particles like gold and silver have a strong collective electronic resonance called a plasmon resonance, and that controls how they interact with light. If the nanoparticle is, if the wavelength of light that's incident on the nanoparticle is not resonant with the electrons, then the light passes through basically unperturbed. But the light interacts very strongly with nanoparticles at the wavelength that corresponds to their resonance, which is an oscillation of the conduction electrons. This is a very important property of all noble metal nanoparticles, and also including the coinage metals. And so this is an example. If I have a gold sphere, a sphere made out of gold, that's about roughly 50 to 100 nanometers in size. The electrons will oscillate at when you shine green light on them, so light at a wavelength of about 520 nanometers or so, will induce a very strong absorption in the nanoparticle. If I take that same structure that's a sphere and I stretch it, I will actually have induced two resonances, which means the electrons can oscillate either on the short axis or the long axis of the nanoparticle. That means I have two resonances, and it also means I can control that resonance where the nanoparticle interacts strongly with light by controlling the nanoparticle geometry. So we can think a little bit further about how nanoparticles interact with light. And once you shine light on a metal nanoparticle, the first thing we could think of is that it heats up. So the light energy dissipates as phonons and vibrations in the lattice of the metal, and that leads to very strong photothermal effects. But that's not the only thing that happens when we shine light on nanoparticles. What also happens is once we set up that coherent oscillation, it decays by exciting hot electrons and hot holes. And those hot holes and electrons are very important because they can do chemistry. So if I have a molecule sitting on the surface of a metal nanoparticle, those hot electrons and holes can be available to transfer into the lowest unoccupied molecular orbital, for example, of the unoccupied orbital of an adsorbate molecule, or the holes can transfer into the highest occupied molecular orbital, which means I can induce charge in the nanoparticle and I can essentially do chemistry. So the intense local fields that are set up by the plasmon resonance, but then also the hot carriers and the photothermal heating are the important phenomena that control how we can actually use metal nanoparticles in applications. So photothermal applications are very common, and so is the greatly expanding application of plasmonic photocatalysis. And I'm going to give you 3 examples today. Excuse me, coming from our work. I'm sorry, I'm burping because I just had breakfast. So, but I'll talk about those during the course of my talk. So the first topic actually has to do with biomedical applications, and that is that if I make a gold nanoparticle into a core shell structure such that the core is not metal at all, but is a dielectric, for example, silica, and then I coat that with a thin gold shell, I can tune the plasmon resonance of the gold away from visible light and into the near infrared. And we discovered we could do this quite some time ago, back before the turn of the century, actually. And we immediately set out to pursue some biomedical applications. And in particular, we found that we could tune the resonance of the nanoparticles, the wavelength that the nanoparticles absorb, wavelength of light the nanoparticles absorb, into a region just beyond visible light called the near infrared. And the near infrared is a region that's also known by bioengineers as the water window. Light transmits through the body maximally in the water window. When we first started this work, there was one water window. Now I believe there are at least 4 water windows further off into the here, and then also further off into the infrared that are used now in areas like brain science. But our interest was just in the first water absorb into a region just beyond visible light called the infrared. Oh, sorry. There's some echo. There's some feedback that just turned on.
Alice, I think you may want to mute.
Something turn on. I can't give my talk if there's an echo like that. Okay, super. Thank you. That was really distracting. So anyway, this is so the water window is where tissue is maximally transparent, and it induces minimal damage to cells of light of that way in that region of wavelengths. So we can tune our nanoparticles to absorb light very strongly at wavelengths of light that basically pass through the body. And so that led us immediately to think about cancer therapy. So I worked extensively with a bioengineer who's now at Duke University, Jennifer West, and we developed a way to basically ablate tumors, remove tumors, using nanoparticles, using these specific types of nanoparticles, nanoshells. And the the first experiments we did, which I'm going to show you, although it was a long time ago, this is exactly how the treatment happens in humans. And this treatment, so in the case of mice, you inject, mice have a tumor on their flanks, and you inject a solution of nanoparticles into their tail vein. It circulates through the body, and after several hours, it takes up naturally in the tumor by a process called the enhanced permeability and retention effect. So the nanoparticles aren't labeled. This is just a property of the tumor vasculature, that the vasculature, the blood vessels in a tumor are chaotic, and they dead end and they open up in a tumor region. So nanoparticles circulating, in fact, drugs are delivered the same way. Drugs that are packaged in a particle that is about 100 nanometers in diameter will, within several hours, will take up into a tumor from the bloodstream. So once the nanoparticles are in place, you shine near infrared light through the skin, passes right through the skin, right directly into the tumor, and there. Oh, okay. Can somebody please stop talking while I'm talking? Somehow this is getting transmitted into my talk. Okay. So this is so at this point, when the nanoparticles are illuminated, then the nanoparticles heat up and they induce tumor remission. So this is what this looks like on the day of treatment. You can see the subcutaneous tumor, and on day 12, the tumor is essentially completely gone, except for a small transient mark left on the skin, which also disappears within a few days. So this is something that excited us very much at the time. This led to trials in humans. It started actually quite some time ago with head and neck cancer, and then this led to a trial in prostate cancer. So it's in the area of prostate cancer that this type of treatment has entered humans. So let me say a little bit about prostate cancer. This is the most common cancer in men other than skin cancer. It's so common, 1 in 9 men will be diagnosed with prostate cancer during their lifetime. It runs in families, so it can be very high probability that if you have a male relative, if you are male and you have a male relative with prostate cancer, you need to watch for this, as your chances of having it is 1 in 3. And it is actually the second most deadly cancer in men because it's not well diagnosed, or if it is diagnosed well, it is not, people do not respond to the diagnosis with therapy in an appropriate manner. And let me explain to you how that works. So diagnosis is basically through measuring something called the prostate-specific antigen, or PSA, in the blood. And if the PSA level is elevated, then people do a biopsy. They insert needles randomly in the prostate, trying to search for what might be a tumor. And here is where you can have misdiagnoses. But if the PSA level is high, the patient enters something called active surveillance, where they just monitor the PSA level. And if they identify that there's a tumor, they go through, and conventionally they go through treatment of radiation and then possibly surgery and chemotherapy for late stage. So these are very, very perturbative to the patient. Once they enter radiation and surgery, they can affect a lot of vital, since it's near a lot of other vital organs, it can affect a lot of vital processes. My dad, who I no longer have, he was a prostate cancer survivor, so I know a great deal about this in tremendous detail. So the problems that can happen is incontinence. You no longer can control your bladder, and also erectile dysfunction is really common among prostate cancer patients, and those affect quality of life pretty tremendously. So the question is, how could nanoshells and how can cancer therapy solve this problem? So the reason that there was that one relied so much on surgery, which caused those tremendously deleterious side effects, is because this is what, when you try to do a biopsy, this is what people saw up until about 10 years ago. They saw that's the prostate. Okay? You see a sphere, but you don't see anything inside the prostate. So you have to randomly go through with needles and try to find where the tumor might be. So that was revolutionized by a group at NIH, and I'll show you one of the members of that group in a minute. where they combined MRI imaging with ultrasound. So, and that's basically software. This is signal processing or image processing breakthrough. But they could see very, very clearly inside the prostate, so they could see precisely where the lesions are located. And they can actually do this in real time. So both Philips and Siemens, the two main companies that do MRI imaging, now have this software where you can directly see and directly place a needle to do the biopsy into the tumor. And so the thought of the people who did this bioimaging, or at least one of them in particular, who was also a surgeon, Art Rostenhad, was if you can place a needle there, you should be able to place a fiber optic there and directly address the tumors, the localized tumors within the prostate. And so the idea, so what I just showed you is something called fusion guided biopsy, which is now the standard, a standard imaging for diagnostics. And Art Rostenhad, who has risen in the ranks of academia since he started this work, was the young guy. He did this when he was before he had a position, young researcher at NIH who was doing this imaging. That's his area, but he's also a surgeon. And he realized that you could form a treatment this way. And so the treatment I described to you with mice, where injecting the nanoparticles into the bloodstream, is precisely the type of treatment that is now being performed in humans. And so he has several cohorts. This is just a small subset now of the people who are also performing this therapy. And to show you what this looks like, this is this is all done within the context of the fusion imaging that I told you. So they set up a grid. On the grid, they know where the tumor is, and they're able to place optical fiber probes into the tumor region. Now, these ablation zones, as this is drawn, are only 8 millimeters in size. This grid is extremely small. I'll show you a little bit more the scale of the grid, but you can see that this is a conventional image of where a prostate tumor would be relative to the urethra and the rectum. So those are very important organs. You don't want to damage those. So this has to be very, very high precision light placement so that the tumor can be addressed. So this is an actual MRI image of how the real estate of the region where the laser catheter is positioned directly between the urethra and then the dark structure that you see, and you see the scale of 1 centimeter. So we're talking about millimeter type precision that has to be is the kind of accuracy that's needed for this type of measurement. So the dark the dark region that you see at the bottom of the image is the rectal wall. So the results of this type of treatment, a radically different treatment than what people have been performing before, are really outstanding. There are 2 trials needed for FDA approval. The first trial was finished in 2019. The pivotal trial, which is the final trial, that's been ongoing since 2020, even though because of COVID, things have slowed down a little bit. They have been able to recruit patients and finish this. The trial still is just wrapping up now. So 2021 will be the final year before FDA approval for this. So I'd like to mention Martin Feeney, who was patient number 1. He went through the procedure just as I described. He only experienced mild discomfort. The procedure was performed on a Tuesday. In other words, on Monday he showed up, he got a nanoshell injection. On Tuesday he showed up and they performed the procedure as I just showed you. And he rode a bike on Friday. We don't know why. He had a romantic weekend with his wife directly after that, which was way more information than we needed to know. But he was very much exemplary of the patients that have been responding to this. They're not seeing any side effects whatsoever. And so this is one of the reasons why this trial's moved forward so rapidly. And the success rate for the first trial at the 12-month point was 94%. So this is obviously very high success rate, a lot of excitement. And now this is being practiced nationally in the United States, on the West Coast, as well as several clinics in the Midwest of the country. So that was story number 1. So just to show you all the different things you can do with nanoparticles and light, we want to address another story that is really important for this century, and it's important globally, and that's the simple fact that 1 billion people in developing countries do not have access to clean water. And we know how important this is also in developed countries, because very often there are failures of infrastructure, and it's very important to make sure to maintain access to clean water. So there's lots of ways to make clean water. People use reverse osmosis, and they use different ways for doing both desalination and cleaning in urban settings, because there's many different types of dirty water. But one of the common themes, and why this is something we should be concerned about, is high energy consumption. So about 50% of the amount of money that's spent on making clean water for you is in the energy that's used to drive these very inefficient processes. And so we thought this would be interesting to see if we could use sunlight to also drive processes, or one particular process of distillation for water treatment. So to understand how this works, I need to talk to you about an old style of desalination. So we'll just focus on desalination today. And this is something called membrane distillation. The idea has been around for decades, and it's so people have known about it. This works in a very simple way. So you have a membrane, and on one side of the membrane, on the top side, where on in my little diagram here, you have salt water. So this is the feed water, and you establish, to make this work, you establish a temperature difference. So between the feed water, so you have to heat the feed water relative to the purified water. So what happens is, when you have a small temperature difference, you have actually an evaporation of water on the hot side of the membrane. So you don't heat it to boiling. The delta T doesn't have to be that large in order to drive this process. But you have water vapor that passes through the membrane, and of course this leaves behind the salt, and the distilled water condenses on the other side. And so it's a very simple idea, right? But the problem is it's really, really expensive, because it takes a lot of energy to heat water. And if the delta T is 0, this process doesn't work. So you have to have hot water, you have to heat all of the input water, what we call the feed water, in order to convert it to the distillate. So we thought it would be interesting to see if we could convert that idea to solar, to a solar method. And so in order to do this, we take the same membrane, but then we coat the membrane with nanoparticles. And so most of you, I'm sure all of you have heard about graphene. Well, carbon black is actually a form of graphene. And so we use carbon black nanoparticles. They're less than 100 nanometers in size. They're very good broadband absorbers, and they're extremely inexpensive. They're made in almost all developing countries as well as developed countries. And so instead of using gold and silver for these types of applications, we use carbon in its graphenic form. So the idea is, instead of heating the salt water, we shine light on this membrane. The nanoparticles heat locally, and so for the water that flows along the membrane, that water is heated locally by the nanoparticles. And then this induces much of a temperature difference between the top layer and the bottom layer, the feed and the distillate, that you're able to actually achieve water vapor, evaporation, and then condensation on the other side. So we call this, so now we've converted the process. We don't have to heat the input water at all by conventional means. We just use sunlight to heat the water. And so we call it nanophotonics enabled, where the nanophotonics is the carbon black particles, solar membrane distillation. So these are some of the initial photos of the first experimental demonstration of this. A tiny little window is exactly the membrane that I'm diagramming on the left-hand side, and of course we have to have pumps and other things and thermometers to monitor the process. So this process works extremely well, and in fact it works in a way that's kind of inverse to the way membrane distillation works. The membrane distillation, remember, as I described it, you have to heat the input water, and then you heat it, and it flows through the membrane, flows across the face of the membrane, and as it flows across the face of the membrane, its temperature drops, right? And eventually delta T goes to 0, and I'm sorry, my dog just joined us. Hi, sweetheart. And the process stops. But if your heat is induced locally on the membrane, when the feed flows in, it starts cold, but then it is heated up as it traverses the membrane, which means the larger you make the unit, the more distillation, the higher the distillate flux, which is the opposite for membrane distillation. With all of the action happens just at the first few centimeters across the membrane, and then there's no more procedure. So no more process. So basically, it scales up. It doesn't scale down. It scales up, which is very exciting. And it's efficient at relatively slow fluid velocities, which is also very important. And also, it's more efficient at higher ambient temperatures. So we're very excited to demonstrate that process. And then we decided to play around with this unit since we saw this wonderful result. So how could we make it more efficient? And so we decided to do something which, in retrospect, as we learned more about it, was actually a very silly thing to do. And we put a lens array on the surface of the nanoparticle laden membrane. So this is just what I showed you before. You have salt water flowing on one side, clean water flowing on the other side. And instead of just having having sunlight incident, you focus the sunlight into little spots on the membrane, which is, in other words, if you have everything focused into small spots, then a lot of the membrane is dark, right? So you only have distillation happening in the region where the nanoparticles are illuminated, which is now tiny little dots on the surface of the membrane. And we tried this with different lenses, and actually what we found was that the distillation, the distillate flux that we're able to achieve went up, and it went up by a lot. It went up by about 50%. And actually, if this was a solar cell, and if you were illuminating a photovoltaic cell, the efficiency would go down because you weren't illuminating this. So we began to realize that the process here is something, of course, it's very different than what happens in a photovoltaic cell. This is all photothermally driven, and we're basically doing chemistry. This is an exponential process. So phase change, as you know, is a Boltzmann dependence. So just by focusing the input light, the distillate increases by 50%. And then we began to look at all the other systems. Lots of other people, as you probably know, many people work on trying to do solar solutions to water treatment. And we saw all of these different references in the literature, and the way that they improved their efficiency was by collecting more and more light and making their units bigger and bigger. But here we had a relatively small unit, and we found with lenses we could actually increase our efficiency to be even better than many other reports in the literature, but we weren't increasing the footprint at all. So just by keeping the unit the same size, and then by focusing light onto it, we were able to actually increase the efficiency by a lot. So how does this work? This works because this depends on the saturation vapor pressure of water, which I mentioned was exponential. And so all of the action happens where the hot spots are, where we focus light onto the membrane. And so this process is, because it's an exponential function of temperature, since photothermal heating is linear, the distillation is actually an exponential function of the light intensity. Right? So we're able to get great gains by doing some very simple modifications that actually teach us a little bit more about how this process works. And then the last improvement, which is also another big improvement, I got to shut my door because this. Forgive me. Forgive me for that. So what we also did was modify the system so that we could actually so that we could capture some of the heat that's transferred from the feed, from the saline feed on top to the distillate, to the clean water below. So every time you have a process of evaporation and condensation, you actually transfer the heat back through the condensation step to the distillate. So you lower the temperature difference by actually doing the process. So we realized if we could just flow this, if we could somehow capture the heat that occurs in the condensation event, we could actually recover a lot of heat, and we could make this an even more efficient process. So what I'm showing you are the actual types of what the panels look like. on the bottom, and I'm also showing you the two main collaborators here, Alessandro Labastri, who is a theorist, who is really the brainchild behind these, does a lot of very detailed multi-physics modeling to understand exactly what happens in one of these solar-driven types of processes, and Pratik Shidangari, who works with him on the experimental side. So the idea is super simple. We had something called a heat exchanger. This sounds a lot like civil engineering, but there's actually some beautiful physics I'm going to tell you in a moment. We add this heat exchanger so that the distillate and the feed have thermal contact with each other, so we can transfer some of that heat that went the wrong way. We can transfer that back to the feed. So what happens when we take our little membrane distillate, and then we add these sections for heat transfer and for heat exchange. And what happens when we add them to our system, I'm showing you sort of the flux as a function of the flow rate of the clean water coming out. When we add the when we add the heat exchanger, what we find is not an improvement. What we actually find is a resonance. So the heat exchanger section and the membrane distillation section couple to each other like two coupled oscillators. And so like two coupled oscillators, they actually have a resonant behavior. And no one had ever realized this before. So somehow it takes a physicist to look at a system that looks a lot like civil engineering and say, oh my goodness, we actually have two coupled oscillators. When you have oscillators like this, you can actually store energy much more efficiently than if you just have a system that's trying to passively store energy. Because you have energy exchange between the two systems, just like the way a pendulum swinging will store energy. Alternatively, will store energy, use energy, store energy, use energy, right, on every swing of the pendulum, storing gravitational energy. Here we're storing thermal energy. And so how does this look? If we look at what's going on inside this system, and we can actually see the heat flow, if we change the rate that the salt water flows, if this flows much faster, then we see there's pretty much strong dissipation of energy. If the clean water flows a lot faster, then there is dissipation of energy. But if the two rates are tied to each other, and that flow is a very important flow, that flow is determined, the optimal flow is determined by the light intensity. So this is a solar process that couples the two flows together as a function of the input light intensity. Then you have all the energy stored in this system, and it stores and it dissipates not over minutes. This is stored by the two fluids, and it's stored for a matter of hours, okay, multiple hours. And so this means that a solar desalination is actually an energy storage device, not unlike a battery, right? But this is all being done with water, right? So we're storing the energy that's captured initially by the sun, stored in the fluids, and they just pass it back and forth to each other, and they're able to continue with desalination over a very long period of time, even if the sunlight disappears. So if the sunlight disappears, like the sun sets, we still can do energy storage. So that's a really important aspect of this basic idea. So the last topic I'm going to talk about has to do with, again, has to do with plasmons. We're going to go back to metals now, and we're going to now talk about chemistry. So the basic idea is that as I mentioned before, metal nanoparticles act as optical antennas. And so what we have been using, typically gold, other people use silver and copper. And we began to think about this particular version of the periodic table, which shows us that some of these metals are relatively rare. If you look at some of these, there might be some metals here that you use as a matter of course in the laboratory, or that are used in commercial products, but you don't often see them displayed this way. And this shows you really that the availability of these, it might not be, the availability might be economic, right? So if something becomes more scarce, it might still be available, but if its price goes up by a factor of 10 or a factor of 20, then you might not want to use this. And we all should need to be thinking about this idea now that we have some elements that are endangered, and we should be thinking ahead to how can we use more sustainable materials that don't have this aspect of being endangered as part of their future. So we decided to focus on aluminum. Aluminum also has a beautiful plasmon resonance that can be tuned across the visible region of the spectrum, as I'll show you in a moment. And so this was one area that we thought was important. And I just showed you carbon, right? Carbon in its graphenic form does have a plasmon and can interact with light. And so this is where, this is my second example of a sustainable plasmonic material. So aluminum is, in its oxide form, is the most common metal at the Earth's surface. So you can see, in terms of its abundance, you can see how much more abundant it is by orders and orders of magnitude relative to silver, gold, and of course palladium. So we're abundant and not rare. That means we'll always be very inexpensive relative to metals like gold and silver, which means the price will always be very much lower. But the properties can be remarkably similar to gold and silver in terms of the plasmon properties. So so the question is, how can we make aluminum nanoparticles? And we thought, well, of course, people have been making metal nanoparticles for many years, many years. We learned how to make gold nanoparticles and also some of the other particles that I made. Typically, you start with a metal ion salt and then you reduce it, and then you cap it with some sort of molecule like a citrate, and you get a pretty picture, and you publish a paper. But all of this is done in aqueous solution, and we realized none of this is at all relevant for making aluminum nanoparticles. So I'm not going to go into the chemistry as much as to tell you that we figured out a way to make aluminum nanocrystals of nicely controlled size, and I'll show you in a moment. We can begin to control the shape. So we do this in a very unusual way. This is made with a catalyst, but it's also made with a combination of the catalyst and specific solvents. And if we tune the solvent mixture, we can actually tune the size from 55 nanometers to over 200 nanometers. So I'm showing you whether we have dioxane on one side or THF. THF, we make large nanoparticles. Dioxane solvent, we make small nanoparticles. And if we mix the two, we can make intermediate sizes. So when we do this, we then have beautiful faceted nanoparticles, and we can then look at their plasmonic properties. As we increase their size, we can redshift their resonance from deep in the UV across to the red region of the spectrum and off into the near infrared for large particle sizes. If we change out the catalyst, we can actually change the shape of the nanoparticle. So this is the only nanoparticle we know of that that requires a catalyst for synthesis, but the catalyst performs also some shape direction in addition to actually catalyzing the nucleation of the nanoparticle itself. So switching gears, so this is an important element and some things I'm going to talk about in a moment. I want to introduce another of these really big challenges that we face as a planet in this century, and that is the cost of chemistry. So the little picture that I have, the photo I have on the right, is a chemical plant in the United States, one of the largest chemical plants. And the numbers that we have for energy they're a little dated because they're only reported once by decade, and it's not required that the industry report these their energy costs. Mostly because the energy has their own, the chemical industry has their own energy grid. So we don't share energy with them. And so they can kind of keep track of their own energy costs themselves. Of course, like any company, they want to reduce their energy costs, which is why there's a lot of interest, of course, in catalysis. But if we just look at the cost of how much energy is needed to make all the chemicals that we use every day, we find that the cost is extraordinary, right? It's 850,000 barrels of oil per day. That's the energy equivalent, and it's a very large energy cost. And of course, we know that some of the processes that we need for life, like making ammonia from nitrogen, this is a process developed more than a century ago, called the Haber-Bosch process, but it consumes about 5% of the world's energy. So there's a lot of interest and a huge amount of motivation really for all of us to be asking the question, how could we pursue more sustainable chemistry to begin to make some of these extremely important industrial processes? So, of course, so Mother Nature has a solution to that. Mother Nature has a lead of a few billion years, of course, to basically, if we think about photosynthesis, right? This is all done by enzymes in plants. And so this is a process that we don't want to necessarily directly model the photosynthetic reaction center, but can we get this basic idea, and can we capture light to do chemistry in a more efficient way than the high temperature, high pressure processes that are used, for example, for making ammonia. So we can do this with plasmonic nanoparticles. So as I mentioned early on in my talk, if you excite the collective electronic resonance in a nanoparticle, like a gold nanoparticle, you have this electron oscillation, and the oscillation decays over a short period of time. And it decays by exciting hot, energetic, or what people call hot electrons, energetic electron hole pairs. So if I put in light of a certain photon energy, the electron hole pairs will have that same photon energy. And so we can see processes where electrons can transfer into the LUMO level of an adsorbate, or we can also see hot hole processes playing a role in various types of chemical reactions. So people have known about this actually for a very long period of time, but it wasn't until we started to use metal nanoparticles and understand this coupling of light between the nanoparticle and between the light field and the nanoparticle, and how to control it, that we could actually start doing this chemistry in a very controlled way. So the bottom line is hot electrons generated by plasmon decay can induce chemical processes. So here's a simple cartoon of the simplest experiment that we could think of for how this happens. So what we're going to do in this experiment is we are going to dissociate hydrogen. Basically, we're going to flow H2 and D2 deuterium molecules across gold nanoparticles. We'll shine light, and if there is a process, if the process happens, if hydrogen dissociation happens, then deuterium dissociation would also happen. It will make HD, right? They'll recombine as HD. They recombine as HD when, and this is a process only induced by light, and we have the following light-induced process. So, and we can do this at room temperature. So we flow H2 over the surface. H2 is very, very stable. There's a very large barrier to dissociation. But we flow this over the surface, and it very, very weakly associates with the gold surface. We can actually then excite the plasmon in the gold nanoparticle. That plasmon will inject a hot electron into the unoccupied orbital of the adsorbate, making it H2 minus. H2 minus, because of Coulomb repulsion, has a much lower barrier to dissociation and can dissociate at room temperature when we use light. And so we see this process, and excuse me, so we see this process happen, and this process can happen at room temperature. So we pursued this, and then we began to think a little bit more big picture about how you can design a catalytic reactor. My dog really wants to join us today, so he's going to join us. Okay, so what I showed you was an antenna, but how can we make this more specific to specific chemical processes? So the plasmonic metals are really great for capturing light, right? For inducing plasmon excitation, and then for generating electron hole pairs through the plasmon decay process. But those are not the metals that we use typically for chemistry. Typically, we use catalytic metals for making catalysts, and many of you might work in this area or know people who have read papers on this particular topic. So many of the transition metals or the more precious metals like ruthenium, platinum, palladium are used for catalysts, but they don't have any interaction at all with light, or they're only very weak interactions, like palladium, very, very weak interaction with light, and only light in the UV. So how can we combine the two? So we have this idea of combining basically an optical antenna. So in this case, we'll use aluminum, right? Aluminum is, as we mentioned before, very abundant and has great plasmonic properties, so we can tune the resonance anywhere we want. And then we put small catalytic islands on the surface. And so we call this idea of antenna reactor. So this is one variation of an antenna reactor. You can also have, as we'll show you, individual atomic sites. You can grow this in different ways. We can also grow this on, also fabricate this type of structure on copper. We could use semiconductors instead of transition metals. But there's different variations. But here we're just going to focus on the idea of an aluminum antenna, and then a catalytic reactor. In our case, we're going to use palladium as our catalyst. And so if we repeat the reaction that I showed you, which was hydrogen dissociation, when we do this just on bare nanocrystals, and one of our panelists today, Linan Zhou, did this work when one of his first experiments he did as a graduate student was find out that you can do this H2 dissociation reaction that we did so nicely on gold. You can also do this on aluminum. Even though aluminum has a thin oxide layer, there's enough porosity that the hydrogen can move to the surface, and one can have charge transfer and dissociation. And so the same reaction, making HD as a function of light, was something you could do with aluminum. But curiously, we also found that it didn't follow the surface plasmon. It followed the interband transition of aluminum, the materials properties of aluminum, where the electrons were most abundant, would actually follow this, would actually induce this chemical process. So if we make the same, take the nanocrystals, and then we put small palladium islands on their surface, which is the time-dependent loop that I'm showing you, this nanoparticle, then we find that, in fact, the process changes a great deal. And now the process is dependent on the plasmon energy. You see this process on the light. So I'm plotting the same, we're plotting the same pristine aluminum nanoparticle on the right, that we have on the right, that we have on the left in red. We're actually plotting this in green. And then we're plotting the same chemical reaction, making HD with on antenna reactor particles. Here we're applying that in the red. And so you see the big difference. So there's a huge difference in HD production, because here now we're following the plasmon, the actual plasmon resonance of the antenna reactor, of the aluminum, right? Not of the palladium. So another example of how another example of how plasmons can control chemical reactions is in this work that was also done by our panelist Linan Zhou when he was a graduate student. And this was studying a very well-known reaction of ammonia decomposition. So this is well known. Everyone understands. People understand the energetics of how this process occurs as an endothermic reaction, and the barrier, the rate limiting step, has to do with the nitrogen. After the ammonia after the hydrogen nitrogen bonds have dissociated from the adsorbate nitrogen, then the rate limiting step is the nitrogen recombining. Sorry, my dog wants to participate in this talk apparently. His name is Fano. Fano, you have an audience today, Fano. Okay, so the rate limiting step is the associative desorption of nitrogen from the surface, and basically this is rate limiting because the nitrogen is occupying the reactive sites on the nanoparticle surface and limiting access for the reactants to then proceed and form products. And so what Linan showed in this work was that light can induce desorption of the nitrogen, and basically induced desorption, the associative desorption step is induced by the hot electrons that are generated in the copper nanoparticle with the ruthenium active sites. And so this looks very complicated, but it's actually very easy to explain. So what he does is he follows the barrier height and how the barrier is reduced by illumination. So if we look at this beautiful contour plot on the right-hand side, we see on the far right-hand side this very high barrier, and that's for the reaction in the dark. And as we turn on the light, the barrier decreases, and we move to the left, and you also see that that barrier decreases with increasing intensity, but it also decreases with in a wavelength-dependent manner. And if we look at the data on the left, you can see the individual barrier heights that were measured for different wavelengths and for different temperatures, so we can measure the barrier height for the wavelength dependence, and then also at the most efficient wavelength, then for the intensity dependence as well. And it's with data like this that the actual reaction barrier was mapped out in this way. Okay, so to change gears a little bit from plasmon enhanced chemistry to what you can do with plasmonic photocatalysts, I could ask this question, and that is, what do all these companies have in common? You might not know, but I'll give you the answer. Anyway, everyone is investing in fuel cells. People consider hydrogen fuel cell vehicles as really the ultimate solution to our problems of CO2 generation, right, of carbon dioxide generation and climate change. And so, of course, a lot of people are beginning to turn towards electric vehicles. But electric vehicles, as you probably know, really have their problems. It depends on the type of electricity that's used to generate the electricity that charges the electric vehicle. So we're still tied to the carbon cycle with electric vehicles, but with fuel cells, we are not tied to this. So if we use a fuel cell, right, a fuel cells basically just, they require hydrogen and oxygen, and they output water, right? And so if we could have a cheap source of hydrogen, then we could certainly facilitate the ultimate goal, which is a hydrogen economy. So looking at inexpensive ways to generate hydrogen is a really critical step. So there's a process in industry called methane reforming, where you start with methane and you convert methane using either water or CO2. I'll show you the little cartoon in a second. Process called methane reforming that gives you hydrogen. But it costs a lot because of all the energy you have to put in to actually make the hydrogen. You have to do this at very high temperatures. There's other processes people have been developing a lot, like electrolysis, water splitting, but there are issues with catalyst stability. And then once you make the hydrogen, you have to deliver it. And even storing hydrogen is a huge research problem, as we know. And so the cost of delivery is really high. So the bottom line is hydrogen is a very, very expensive game. If we look at the price, so hydrogen right now, if you have a hydrogen fuel cell vehicle, and very few people do, they actually subsidize, the maker of the vehicle subsidizes the cost of hydrogen, and it's roughly cost 4 times the amount of fossil fuels. So where it's not even competitive, even getting close to competitive. So how could we solve this problem? So we can solve this problem with nanoparticles and light, of course, right? Our theme of the morning. Or of the evening, excuse me. So if we start with methane reforming, in this case with steam methane reforming, so you use water vapor and methane, and you convert you convert the methane to form hydrogen and also carbon monoxide. So this process is typically done in industry at very high temperatures. So that requires not only the energy to get to these very high temperatures, and of course it requires fossil fuel to drive the high temperatures, but it also requires a lot of capital equipment. You have to use big steel vessels and so on to get to these very high temperatures, to sustain the high temperatures. So instead, what if we use light? So the same process, excuse me, of methane reforming, if we do this based on the photocatalysis that I just showed you a few minutes ago, we can actually do the process not at 600 or 900 degrees, but at 200 degrees. Well, 200 degrees, first of all, it saves you a lot of energy. The way that we can do this at 200 degrees is with light, and one of the most important breakthroughs here is really cheap photons, so solid state lighting actually provides very, very high efficiency cheap photons in order to do the photocatalysis, but you have to figure out how to build a light-based reactor to do it. So you can do this at 200 degrees Celsius, and 200 degrees Celsius you can do in your oven at home, right? Many types of materials can sustain a reaction at 200 degrees Celsius. So, and there's ample opportunities also for other renewable energy sources to drive this particular reaction. So a company was started based on this idea of plasmonic photocatalysis taken in the direction of engineering, so we don't have heat-based thermocatalysis, but instead we have light-based catalysis at much more mild temperatures. And that company's in Houston called Syzygy Plasmonics. And so their estimate, as you look at all of the cost of hydrogen, is that if you make hydrogen by this very new process, you really drop the cost of both of the hydrogen and also of the production equipment, because you don't have to have enormous facilities that take advantage of the economy of scale. And you also don't have to have very large, very, very heavy steel equipment and so on for sustaining these very, very high temperatures. So this is ancient data. This doesn't show at all what their current production capabilities are, but it shows you what happens when you do chemistry with light. And that is when you turn off the light, the chemistry stops. When you turn on the light, the chemistry starts. It's very different from thermocatalysis, where it might take them days to turn down or days to turn on a reactor. You have to keep the reactors going all the time. For light-based synthesis, you turn it on, you get your hydrogen, and then you turn it off. So it's a very different, very much more facile type of chemical process. So this is something that I think is going to be really revolutionary in terms of making different types of chemicals. So I've talked about several different topics today. Prostate cancer therapy, and this is Art Rostenhod with patient number 1 and patient number 1's wife. I talked to you about solar desalination and how we can increase the efficiencies by you doing some very simple things and by realizing what physics is also built into these very interesting types of structures. I mentioned some earth-abundant plasmonics, which is very useful for getting us to the point of doing plasmon-induced chemistry. And this is actually the CEO, Trevor Best, the CEO of Syzygy, and they are pursuing hydrogen on demand. So with that, I want to thank you for your attendance and also thank the many people who worked with us. This is a snapshot of my research group a few years ago. You can see Linan standing prominently in the front line, and well, many of these people have now graduated and gone off to very productive, exciting careers. And some of them are still are finishing up, and some of the new people have replaced them. So that's our story. Thank you very much.
Terrific. Thank you so much. I think you can hear a few 100,000 people clapping around the world if you could listen in on the internet right now. We have some questions that have been sent in from the audience. I'm sorry that we can't get to all of them, but we'll try and capture additional ones during the panel discussion that follows. The first one is, in the resonant capture and storage of energy in your solar distillation work, how important is the sharpness of the resonance, and can that be controlled?
That is a very good question, because you hear a lot about the Q of an oscillator and so on. And this is that in this particular resonant process, it's a dynamical energy exchange. So how can I say? So the resonant energy exchange that I showed you is the Q is not the plasmon Q. The Q is related to the system and the time scales within the system for energy exchange. So like all resonators, that Q, which I showed you earlier on in my talk in terms of the plotted with an x-axis of the distillate flow rate, that Q is important, of course, and it's controlled by the system. It's controlled by the loss I'm sorry, I have to shut this door again.
You should have a little please stand by music. There you go.
My apologies, but the problem is this alarm is going off, and it's gotten my dog very upset because he doesn't like noises like that. So that's he keeps opening the door and distracting us. So basically, the flow rate is the Q of the Q of the system is of course important, and that's controlled by the loss of the system. So things like insulating the system in certain ways and making that efficient at that kind of level, at the sort of the engineering level, is what's important in that particular process.
Very good. Let's see the next question from Xiangkun Elvis at the Institute of Modern Optics. Nano effects using noble nanoparticles, especially SPP and SPR, have been developed for decades. So is it possible that there remain surprises in the theory of these nano effects that can be discovered and perhaps applied?
That's a really good, that's a very, very important point, because, you know, we got involved in this field years and years ago. And yes, you know, we're taking advantage of the fact that some of the properties are extremely well known and can be calculated very precisely, right? So we're, you know, that's one of the reasons why I think applications are emerging, is because there are so many aspects that are very well known. There are certainly, as you know, there's always, science is always surprising us, right? We are operating, for the applications I showed you, we're operating in a regime where we can rely on very well understood, very well known, very well understood science. In terms of surprises, there certainly are new materials where we see plasmonic effects, right? There are reduced dimensionality materials. There are semiconducting materials. There could certainly be some interesting regimes where we could see some new physical phenomena. And so in the, you know, for sort of the standard way many people start their experiments with 100 nanometer size spheres of silver, they're not in a parameter space where there probably will be surprises. So moving to different dimensions, different structures, different materials, one should always be aware that there might be some interesting new phenomena.
Very nice. Our next question,
Thank you.
Is we're taught that photons are expensive for chemical synthesis. So can you comment on the comparison with nature, which can afford to be rather inefficient?
So yes. So when I began to talk about this type of chemistry with some of my physical chemistry, chemical physics professional colleagues at different universities, some of them are very familiar with doing quantum chemistry with lasers, and those are extremely expensive photons. But the big breakthrough here is solid state lighting, right? We now use LEDs that have efficiencies above 80%. So if you have an electrical source, you can certainly have a photon source. And so in that sense, none of this would really make any kind of economic sense if we didn't stand on the shoulders of the people who were doing who did solid state lighting a couple decades before. So that work was really important for making this work happen. Is critically important. So we hear a lot about about running reactions in sunlight. There are issues with sunlight. I love solar things. Of course, we pursue a lot of solar applications, but solar is solar is, of course, affected by nighttime. It's affected by clouds. Right? The chemical processes, again, are exponential processes, and so cloudy days are not very good. It's very different from photovoltaic cells. I can be in Seattle, Washington, or in other places that are large, many cloudy days per year, and I can still put solar cells on my roof. Some of these other processes I cannot be running efficiently because if a cloud passes the sun, the process drops to 5% of what it is when the sun, when the sun is directly incident on the process. So in that sense, the people who taught you that photons are expensive were correct. They weren't really knowledgeable about using more modern, less expensive solid state lighting sources. And I think that the issues of solar speak to themselves. There might be more efficient ways to be doing these processes with solar energy, but those have yet to be pursued.
Thank you. And our final question from the field is from Linghui Chu at Shandong University. For aluminum nanomaterials, especially for nanoparticles, will the local field enhancement around the aluminum nanoparticles be much lower than for gold or silver nanoparticles?
Excellent question. So the answer is no and yes. Okay, so the answer is no, because if you just compare a bare aluminum nanoparticle with a bare silver or a bare gold, also of high purity for all those materials, you will find that the fields are quite strong. Okay, so field enhancement is going to be about the same. The issue with aluminum is that it is always terminated by a native oxide that's between 2 and 4 nanometers thick. And so if you take for example, 2 nanoparticles in close proximity, right? This is sort of the model for a lot of people who study local field enhancements for surface enhanced Raman scattering, for example. You always have, with aluminum, you're going to always have this layer of oxide on each particle. So there's an automatic spacing where you're not going to be able to bring the particles closer together in practical applications. I mean, in an ultra-high vacuum, that might be different, but aluminum is so incredibly reactive that even in ultra-high vacuum, the oxygen will find its way to the aluminum surface, which is why this is not something that was done in all the days when people did ultra-high vacuum surface science experiments. So the answer is, so the practical answer is it will always be lower, but if you design it well, so if you wanted to design a sort of substrate, you can do this, but you cannot expect to be getting the sensitivity that you would sort of at the single molecule sensitivity level. So, but what is interesting is that there's many applications where you don't require single molecule sensitivity. Your threshold for how sensitive the detection system, chemical detection system is much the threshold is higher, so or lower depending on how you see that, and so there certainly are possibilities of using aluminum nanoparticles for sensing. Especially because they're inexpensive, right? They're unbelievable. They will always be very inexpensive, and you never have to recover the metal because aluminum just converts to aluminum oxide, which is dust, right? Which is in our environment. So in that sense, they're very environmentally sustainable. But yes, there's a cost inherent to the fact that these are more reactive metals. Thanks.
Thank you. And now what we'll do, we'll bring out our panelists. We have Dr. Linan Zhou, who we've heard about quite a bit already during the talk. He got his PhD at Rice University and was a postdoc there, and then the chief scientist of the company we heard about during the talk, Syzygy Plasmonics. And he recently, last December, moved to South China University of Technology, where he's pursuing research in photocatalysis, electrocatalysis, and spin catalysis. He's won the Reactor prize and many other awards. And then we'll also bring out Xiangkun Elvis Cao, who's a PhD candidate in mechanical engineering at Cornell University, also quite an inventor. He's won a whole series of prizes in entrepreneurship, science, and engineering. And so please come out and join us. I have you separate there, right? Very good. And hi. Let's all have our cameras on, and we should appear redistributed properly in this. Yeah, there we are. Great. So let's start with Xiangkun.
Sure. Thanks, Paul, for the very nice introduction. And Naomi, I really enjoy your talk. And currently, I'm a 5th-year PhD candidate, and I'm Cornell University in Ithaca, New York. And today, I think as a young researcher in the renewable energy sector, I'm pretty interested in the photocatalytic applications of the plasmonic process, which you described in your talk. You mentioned about the membrane distillation is not scalable as a single unit. And my first question is also centered around scalability. And what do you think we can do to increase the scalability for the plasmonic photocatalysis process? And can you provide some insights on how to increase the scale-up potential therefore more potential for commercial applications from the perspectives of both catalyst development and reactor engineering? I guess it's pretty long, but it's centered around scalability.
Okay. So basically, so first of all, perhaps I misspoke, or so membrane distillation. So solar membrane distillation is scalable, right? The larger you make the system, the more efficient it is. So that's unlike conventional membrane distillation. So I just wanted to make sure that that was clear, that process is scalable. So in terms of chemistry, so we've been looking at, as a research lab, right, we're looking at the actual nanoparticles themselves, and we're not worried that much about the efficiency of the process as it would be translated into an industrial scale. But to translate it into an industrial scale requires the development of reactors that use light and use light efficiently. So in optics, one knows lots of different ways that one can illuminate samples. One can worry about light scattering and use multiple multi-pass cavity type configurations for using every photon. But those are processes well known in optics, and they're not particularly well. They're definitely not well known in chemical engineering. Chemical engineers learn a lot of different things, but the one thing that's left out of their already very extensive curriculum is optics, typically. So this is a field that's really going to require the convergence of optics ideas into the idea of chemical reactor design. So it's very exciting. It's very exciting to see that folks are now just starting to work on this in academia. Certainly the commercial entities that are certainly the company that was founded based on this has done extensive work on reactor design. So that's I think a really important aspect of making any of these ideas work.
Okay, thanks, Naomi. And when speaking about the reactor, what do you think would be some good insights over the design and the design considerations in generating or designing light-based reactors? Is there something you can share there? Because I'm working on reactor design for CO2 conversion for light-based applications, and it would be really helpful to listen to your thoughts as well.
Well, I don't work on reactor design. That's other than what we're doing. We work almost completely focusing on understanding the chemical reaction, right? Which is also extremely important. I mean, this field is growing rapidly, and you see a lot of papers in the literature where people, once a group begins to demonstrate that there are important non-thermal processes, that hot electrons might take a role in certain types of chemical reactions, then in some people's eyes, everything becomes a hot electron-driven reaction. And then there's a backlash where there's no such thing as hot electrons and everything must be thermally driven. So you see people making these these sort of hyperbolic arguments on one side or on the other side, when of course what happens is both processes can happen in any given reaction, or sometimes you have completely thermal processes. So one thing that I think is important is, this is really, as far as I'm concerned, is a really absolutely major new field within chemistry, is to really understand how to do this, how to drive light-given reactions. But it's also really, really important to understand the fundamental science and how some reactions will require this non-thermal component. The non-thermal component will be the major mechanism for increasing efficiencies relative to thermocatalysis. But then some other reactions that you might want to be pursuing will have no hot electron or hot hole component, and will basically be completely photothermally driven processes. So it might be that what one needs to be thinking about in terms of reactor design is what kind of reaction are you going to pursue, and that might be dictating how you specifically design a reactor. So yeah.
All right, thank you.
Let's move over to Linan Zhou.
Hi.
Oh, go ahead. You have a question.
No. Maybe I just get a little bit comment on Xiangkun's question about that. The comment on the potential of this technology and also reactor, something like that. I'm not an expert of the reactor either, but when I did the research in Halas group, focus really on the fundamental research and also the catalyst development. And one thing I want to emphasize a little bit about that is the fundamental research. I would say is the very important part of pushing this technology to be commercializable. because quite nowadays, I would say looking for a good catalyst still quite relies on trial and error, and understanding the mechanism will get us out of this kind of trial and error and really be able to design from the theoretical side, which is why it's so important to understand that in the lab. And I was maybe make it to a little bit extreme is that it's the only way we can finally make this technology be able to put onto the market. About a reactor, based on my experience in the company, I think they do quite a very good job actually. They have some very new technology that I never heard when I was in the lab, that's really about the engineering side, but I think that is something I don't worry too much about, actually about the catalyst and how to develop even better one, really focus on the fundamental side and really understand the theory under that and all the factors of better catalyst. That's why we start from a very simple system, right? And instead of focusing on efficiency directly, but focus on the fundamental and finally goes to the efficiency is the kind of the rule go over there. Yeah.
Yeah, if I think those are great comments, Linan. If I can think a little bit also another aspect of this, when you focus on the fundamentals, you also conceive, so invariably we're always looking at the wavelength dependence. And we find in the lab what wavelengths do we have the greatest efficiency. But so that is going to be very important for reactor design. But reactor design can also go the other way and say, hey, our reactor is built to run on green light. You have to optimize your catalyst so that it's most efficient at green light, right? So that means changing nanoparticle size. So the two ideas of reactor design and catalyst design actually, there's an interaction there between the two, which is why this is a very new field, right? And why, companies will rise and fall based on their the strength of their understanding of how much you need to basically base the reactor design on the catalyst, but then base the catalyst design on the reactor and kind of converge both of them to really get highest efficiencies for any given chemical reaction. Right, so it's very different than the sort of the generic, here's my reactor and I can do anything in this reactor because I can put in a lot of temperature. We had a situation back when Linan was a graduate student where we sent some catalyst particles to do a certain reaction. We were very excited about it. Linan spent several weeks making these particles. We sent them to these people, and they came back and said, they don't work. These don't work. Your catalysts don't work. We're like, that's crazy. Of course they work. They work really well. And so what wavelength did you use? And they said, wavelength?
Yeah, so basically you need to understand it, right? And when you use the right apparatus and something like that, you need to make a reactor resonant with your catalyst, and so they couple each other to exploit their most efficient way, basically. Yeah, absolutely.
Maybe going back to that earlier question, can you comment on where you target the photochemical efficiency to be? So you can create photons very efficiently now. How well can those be converted into, a reaction stoichiometry, or I don't know what the right term is there, but yeah.
Right. Well, in many ways, that's dictated by the economics and the commercialization already of solid state lighting sources and solid state lighting companies, right? So we know that there's certain, if you make solid state white light sources, right? This is done using a blue source and with a yellow filter, right? That's how we get white light. So that blue source would be a good starting point. And then there are other sources as well that are mass produced and that are used. So where the production makes them incredibly, incredibly inexpensive. Most of them are in the visible region of the spectrum. And so that's really where we're focusing for this. And also the energetics of the plasmonic photocatalyst process is such that many of the charge transfer processes would work very, very well with, just generally speaking, with photons in the visible region of the spectrum. So that gives us kind of a very, very productive but limited region that we can focus on for developing higher efficiencies.
Yeah, I guess I have a follow-up question. Because during your talk, you chatted a lot about the advantages of plasmonic photocatalysis apparently. And my question is, how do you evaluate the greatest barriers or disadvantages of plasmonic photocatalysis, and what are the possible pathways that you can think to overcome these barriers in this field?
That's a very broad question. I don't mean I'm not laughing at you, but that was an extremely, extremely broad question. It's hard for me to sort of get my brain around it. I guess, you know, when you're doing research, you don't think about what the disadvantages are. You think about them more as challenges, right? So there's some things we know. So, you know, for example, you know, what people have always dreamed about was selective bond breaking. And what we're doing really is, in many contexts, we're doing selective bond breaking. But as this field develops, we're also beginning to realize, what does plasmonic photocatalysis do well in the terms of fundamental chemical phenomena? One thing that it does really well is that it assists the process, or stimulates the process of desorption. So once I have an adsorbate on the surface of my plasmonic catalyst, whatever chemistry might happen, then the energetic electron that's formed inside the metal will actually induce a desorption process with high efficiency. And we know this because it's an electron-driven process, right? So the thing that makes this so efficient relative to our traditional idea of photocatalysis, which is, you know, some molecular complex and a photon, right, is that these processes are driven by, are basic electron-driven processes. They have a much larger cross-section than photon processes, and so this sorry. And so this is going to be very important as we develop more efficient types of processes. So, or for each particular chemical reaction, to see how we can improve the efficiencies.
Thanks.
Well, one of the things that the students and postdocs in our audience like to hear about is how you choose people for your research group and your companies. How do you find the next Linan?
It's a two-way process. I mean, sometimes, so one thing that's very important in research is passion, right? Is you have to be hot, you have to love the research you do. You have to really, you know, that's the whole process of graduate education, is to go from an undergraduate who is taught a lot of stuff, so you're this passive repository of learning, and then you also, through that, you become, in science and engineering, you're a problem-solving machine. You know how to solve every problem. Give me a problem set, I'll solve a problem. You have a problem set, I'll solve a problem. But then you have to learn how to go from that point to how to ask the questions, right, and how to actually produce research, not just learn about research from others. How do you actually produce it yourself? That's a transition that is, it's a transition, right? Some people go to graduate school and they actually don't sort of make that transition. They still sort of have an undergraduate mindset, and that's a failure of their graduate education, right? Graduate education means you should be generating research ideas, right? You should have a passion for, you're thinking about a research problem. It wakes you up at 2 o'clock at night, right? Because it's in your dreams, and it wakes you up at 2 o'clock, and you have ideas for now how I can solve this how can I solve this problem? How can I solve this process? And so that's a natural output of research and of the transition through as you become a professional researcher. So in terms of students, sometimes students come to you that way, where they're really hungry and they really want to be working on something, but then sometimes you see them work on something and then they catch fire, because they're not really sure how this all graduate education stuff is supposed to go. But then they realize, through their peers around them and through their own affection for and their own interest in the science that they're doing, that they become more and more fascinated by it, more and more excited about it, and that passion just envelops themselves. Right? So you see, because you see this happen in different types of people, there is no sort of one single criteria. I would wish that there was, but sometimes some of my best students are ones who came to me and they seemed good, but then a year later they were like 10 times more interested and more motivated and more excited about what they were doing than when they started, because they caught fire, right? They got it. Right? And that's something that, you know, so there's no hard and fast rule, but I think for any students who are thinking about that's the process. That's the transformation that you go through in graduate education. You go from somebody who's given tasks to somebody who can give tasks, right? Because you know what the next steps are. So learning how to do that is part of your own personal journey for how you do that.
Yeah, so just some opinion on this one. So because I just become a independent investigator, and very recently I was thinking about how to make a group grad. You know, something that you don't think about it when you were a graduate student because you focus very on research. But when you become an independent advisor, you now think about that things from this viewpoint. And Naomi just mentioned about the personal things, which is really important for a person to be self-driving to doing things and really enthusiastic in their research, something like that. But another aspect I can feel probably, especially for students, is really from the group environment, the whole thing. You know, for example, in Halas group, it's really a supported a group because we have people from different areas, people from chemists, people from physics, people from bios, and people from different education and research background. They connect to each other. They always generate some good ideas, something like that. And I think a group with a really good environment will kind of self-attract good people. Rather than just good people, rather than you looking for good people, actually good people attracted by you to this kind of group environment, and they get the environment really makes people good rather than just by itself, you know. So I really want to point this one out because that's kind of my self-feeling when I was a graduate or even when I was undergraduate, because my undergraduate group is also a really nice one. Yeah, thank you.
Terrific. Thank you so much. And I think let me close the panel and let me do what we might normally be able to do across the stage, which is to thank Professor Naomi Halas, and there would be a plaque and we would get to see each other and we would be going out somewhere afterwards, but we'll postpone that for the moment. And thank you for this just beautiful lecture and description of your work over the last few years, and we're looking forward to seeing what it is that you do next. So thank you from all of us and from the broad audience around the world.
Thank you. Thank you so much.
Thank you very much. Thank you very much.
And coming up at iCANX in April, we have actually another friend, longtime friend, Rod Ruoff, sat next to me in high school in Ithaca, speaking back to one of our panelists, and then our ACS Nano Rising Star lectures and more great talks for April. So be sure to tune in the coming 4 weeks. Yeah. Oh, sorry. Back to here. And yeah, next week in particular, Rod Ruoff with Alice and I and Jagadish will all host together with our panelist Bing-Ha Wang from University of Tokyo. And we have this growing family of speakers connecting the world together through science. And I especially want to thank Professor Alice Zhang again for organizing these amazing seminars and giving us a chance to see each other and meet together virtually, and looking forward to the time when we can do that again in person. So thank you once again, and good evening, afternoon, morning, depending upon where you are in the world. And thank you for joining us today.
Thank you.